A developer spins up a small, open-source language model on their local desktop. To keep the outputs factual, they wrap the model in heavily engineered system prompts, defining strict boundaries and rules. But applying external pressure to a constrained environment inevitably leads to fractures. Housing a smaller language model entirely on your own hardware offers privacy, but it provides zero inherent protection against fabricated outputs. In this split-screen comparison, we give two models identical, complex constraints. The small model on the left immediately generates a fast, highly confident block of text that is completely fabricated. The large model on the right produces a heavily structured, accurate response. A common misconception attributes the small model's failure to careless generation or a poorly written prompt by the developer. The reality is a matter of architecture. A small model hallucinating is a structural inevitability driven by three specific factors: less stored knowledge, weaker reasoning chains, and poor uncertainty handling. Reducing a model's parameter size limits its factual reasoning engines, creating an architectural deficit that prompt engineering cannot easily overcome. To understand why this happens, we have to look at parameter size as a form of data compression. This network graph represents the architecture of a massive language model. Operating in a low compression state allows it to retain high-resolution relationships between billions of data points. When you ask a question, it navigates this dense memory network to find an unbroken, high-resolution match. Fitting a model onto consumer desktop hardware requires stripping away parameters, a process called parameter compression. This extreme compression destroys detailed data relationships, manifesting directly as missing facts and empty structural gaps. The point of failure arrives when a user queries the small model about a subject that now falls into one of these gaps. The model still attempts to answer. To bridge the void, it improvises content that structurally sounds correct but has zero factual basis. Lacking the necessary data density to map a true connection, the model defaults to predicting the most statistically likely grammatical sequence. When that statistically likely sequence arrives on the front end of your application, you perceive it as a hallucination. In these highly compressed architectures, data voids are filled by fabricated guesses that mimic the structure of accuracy. Language models do not possess an internal database of true or false facts. They are probability engines executing sequential predictions. A perfect sequential prediction flows logically down multiple diverging branches without error. Large models are calibrated to recognize the difference between a sequence that is factually true and one that merely looks structurally correct. Small models lack this pattern discrimination. They routinely overweight surface-level grammar, preferring paths simply because the syntax appears correct. This logic tree illustrates the steps required to fulfill a complex prompt. The inability to distinguish true facts from plausible syntax creates severe failures here. The large model recognizes subtle inconsistencies at each junction, staying on the correct path to the objective. When we assign the exact same multi-step task to a small model, the mechanics change. It begins accurately, but immediately loses track of the original context across successive steps. This is reasoning drift. The model abandons logical constraints mid-generation to chase a plausible-sounding tangent. At this stage, the model has stopped answering your prompt and is only generating text to align with its new trajectory. Once this drift begins, it is virtually impossible to stop. The model's context window becomes poisoned by the outputs of its own previous steps. Severe hallucinations emerge as compounding, cascading collapses of logical tracking across multiple steps. To counter this drift, developers turn to external constraints: clear instructions, system prompts, and strict operational boundaries. This boundary box represents the assumption that placing strict limits around a local model will contain its output and enforce accuracy. Architecturally, a large model is equipped to follow these paths, but small models lack the continuous attention capacity required to hold external constraints in memory over a long generation. Despite explicit instructions, the small model ignores the defined path. This constraint failure is driven by a specific missing component: uncertainty calibration. Large models have the capacity to evaluate their own knowledge gaps and recognize when they are hitting a defined boundary. When they reach that limit, they are highly likely to halt generation safely, returning statements like, "I am not sure," or "this may be incorrect." Small models fall into a confidence trap. They do not know when they lack information. Without an internal uncertainty meter to trigger a halt, they default to answering every query with absolute blind confidence. This makes small model hallucinations particularly dangerous for enterprise applications, where a fully fabricated answer arrives formatted to look highly authoritative. You cannot command an AI to respect a boundary it lacks the capacity to remember. Looking at these inference pathways side by side, the mechanics of hallucination become clear. A model fabricates information whenever it must choose a path forward, but lacks the internal signal to choose correctly. Due to heavy parameter compression, small models operate in a continuous state of low signal. This is the signal-to-path deficit. Operating in a constant deficit strips away the model's structural control over the sequences it ultimately selects. Hallucinations represent deterministic outcomes of an architecture locking into place. Small models hallucinate because their Heimlich-compressed architectures provide them fewer valid logical paths. This structural reality dictates the fabricated paths they are forced to choose, regardless of the prompt used. Ultimately, small models simply possess vastly weaker structural control over the sequences they generate.